Okay, so first of all, thank you for letting me show our results here. So what I will show you today is the recent results about the transfer rate of the muon to carbon and a short overview about the next data taking. What is the aim of this experiment? Okay, the search for fundamental physics about the proton. So we have already widely saw the way through the scattering and the spectroscopy. So what we do is a measurement through the spectroscopy of exotic atom. In fact, what we want to analyze is the muonic atom. And why do we use the muonic atom? Concerning the factor that is the ratio between the reduced mass of the muonic atom over the reduced mass of the electronic atom, we know that the hyperfine splitting is enhanced by the square of this factor. So the aim of this experiment is to measure the hyperfine splitting, and it will allow also a measurement of the Zemach radius. So, okay, here we can see a scheme about the method that is used in FAMU. So we have a mixture of a gas where is present hydrogen and a IZ element, for instance, oxygen or carbon, like in this case. So we inject a muon beam inside the gas. And what happens is an excitation and a combination of the muon with the proton. And after the thermalization of this muonic atom, that is a deceleration of this muonic atom, we inject a laser, trying to be as close as possible to the hyperfine splitting. So what happens is a change between the state F equal to 0 to F equal to 1 of the muonic atom. And after collision with the rest elements of hydrogen, what happens is that the muonic atom acquire a kinetic energy due to the conservation of momentum and energy. So after that, there is the transfer of the muon to the IZ element. So after this transfer, what happens is the emission of X-rays from the IZ element. So the more the X-rays we measure, the more are the muonic atom, and the closest we need for performing the experiment. So here we can the pulsing beam and the distance between the two spills. Here we have two spills. That means that for each data taking we have 2 pulses. Here we can see not the final setup of the experiment, but the setup regarding the measurement that I'm going to show you regarding the transfer factor, the transfer rate. So we can see here that on the right here, more or less here, is the target where as methan this cavity. We have the lanthanum bromide scintillating detector. These are fast enough and are read by PMTs. And here we can see in red the muon beam entering inside the cavity. So okay, concerning the data, we have so this as mixture where the methane is present at 0.3%, and what we explored is for temperature. So here we can see the distribution, the temperature as a function of the time of the run. So mainly for temperature function of the time after triggers. So for waiting for the thermalization of the muonic atom. So we don't want what we call the prompt emission. We are searching for the delayed one. Here is an example of the waveform that we obtain as a signal. So here the scale of time is nanosecond. Here in some cuts in order to reconstruct the signal. I do not enter into the details. You can find here the list of the cuts. And what we do is the analysis, the counts of the X-rays in different times after the trigger. So here we have 7 time intervals corresponding more or less at this region. And what we expect is an exponential decrease. We can extract the transfer rate, as we can see in further detail later. And so we fit these maxima coming most of all from nickel and aluminum, the elements present in the target, in order to calibrate the and comparing it with the real energy of this maxima, we can obtain the fit of the calibration of the detector. We do the same with the but the delay region that we saw just actually we have a free maxima. The Ki alpha here are resolvable that we can plot it here. And doing the comparison that I told you about, we can obtain the calibration of the detector. So we can see here that is pretty linear. After calibrating the detector, we can obtain the same distribution that we have here, but in terms of kilo electron volts. So what we can see here is this distribution as a function of the time interval with the correction in efficiency and lifetime, but anyway, these are close to 100%. And what we can see here is the blue line that is the signal that comes from the sample with the methane and hydrogen. And in red, we have the signal coming only from the hydrogen. So we do the run also with the only hydrogen in order to subtract the background from the sample with the signal. So what we do is between the blue line and the red area, and we calculate the integral between 50 kilo electron volt and 100 kilo electron volt, where we have our K alpha, K beta, and K gamma from carbon. And what we do, so it's obtaining the counts of gamma rays. So this number is the number of X-rays that we obtain. And we obtain this number for each one of this time interval. This is an example at 200 Kelvin. So for these 7 points coming from the difference of these 7 plots. And from this, we can extract the transfer rate. The formula is this one. We know that there is an exponential decrease. And we know that the argument of the exponential is a function of the element component. Among them, there is also the transfer rate to carbon. So fitting with this step function, this behavior, we can extract the lambda, and from that we can obtain one value from the transfer rate, one value for each temperature. So we have 4 temperatures, and so what we obtain is this one. Is a pretty stable constant transfer rate that is actually not exactly what we want, because we would like to have a transfer rate as a function of energy, like happens for oxygen, because in that case, we know that changing the energy, the more is the energy, the more is the transfer rate splitting. This is a bit higher with respect to the other one. Unfortunately, for the carbon rate, we do not have for the moment any theoretical prediction, but okay, we are working on that. What we can do is to compare the previous results of oxygen. So what we have here is the behavior of oxygen. The black dots are from oxygen, and the red ones are the new results coming from the carbon. So we can see instead that oxygen is increasing as a function of temperature, so as a function of energy. That it's what we want. And this is also quite in agreement with theory. I don't put the theoretical lines, but okay, there are some models in agreement with that. Okay, so this is for what concern the recent results. Next fall, we scheduled a new data taking. In this case, what we want to obtain is a real measurement of the hyperfine splitting with the presence also of the laser. So this is on the right a sketch of what we expect by this run. We will scan the difference of frequency around the hyperfine splitting, and what we expect is to have more signal closer to the hyperfine splitting. So the data taking will last more or less 1 month, and for each one of the day, we will take data frequency. So we expect a run of 30 frequency values. So okay, we can see that the red points that we can see here in this sketch. So this is not a simulation; is that just explicative? The red point is the difference between the signal, so the same signal that we saw here. The difference between the signal with the laser minus the signal without the laser. So obviously what we expect is that in proximity of the hyperfine splitting, that in search is the signal coming from the delayed region. So in order to wait for the thermalization of the muonic atom. So also in this case, what we want to take is a signal after more or less 1000 nanoseconds. And here you can see again the highest concentration due to the presence of the beam pulses. Here instead, on the right, we have a simulation of what we expect a signal. So for the moment, we just have a simulation. And here, the dark blue distribution of signal plus background coming from the laser, and in the light blue, we have just the signal without the laser. In this case, we expect to control the systematics, even if we expect to have a bigger number of systematics due to the fact that the run will last 30 days. But what we can conclude is that the recent results confirms the effectiveness of the detection system in a pulsed intense beams. We saw that the carbon transfer rate is not so different in terms of values from the transfer rate of the oxygen, but we don't see for the carbon transfer rate an increase in temperature as we saw for the oxygen. So it will let us probably to choose the oxygen instead of. Some of this analysis is also to optimize all the parameters, above all in terms of the gas mixture. So not only in terms of which elements, but also the percentage of the element inside the admixture, the pressure, and the temperature, and so on. But anyway, so this is we are ready for the next data taking. that will be held next fall. So from my side, that's all. Thank you for the attention.
Thank you, Simone. So, yes.
Thank you for the talk. So I was wondering, so you said you will take 30 frequency points.
Yes.
So what's your line width and what's the accuracy that you are aiming?
The accuracy, okay. What we want to explore is an energy interval of around 0.1 milli-electron volt. This corresponds to an interval range of frequency of some gigahertz in terms of the laser. And we have, okay, an accuracy about the laser of the order of 0.1 gigahertz. So this is what we expect. But okay, the purpose of the experiment is to do several several runs. So the first one will be wider in order to define the constraints, and then in the following ones we want to be more tight in terms of the right frequency.
But the uncertainty is almost like 40 gigahertz in the line, in the theoretical determination. And if you scan 30 points at 100 megahertz, as you say, like the line width is 0.1 gigahertz, yes?
Yes, yes. Is so more or less is 10 of the gigahertz, the total range that yes, the first one is on time. In the short time is not to define precisely with the high accuracy the hyperfine, and then repeat also with with a finer also accuracy of the scanner.
So the difference between one step and the other probably will be few gigahertz, right?
Yes.
Okay, my second question was about the, you are counting mainly the X-rays.
Yes.
So what about the X-rays that come from the muon decay and the electrons that will give you these X-rays?
Okay.
Specifically when you have this signal that you show at the end.
Okay, in fact, here you can see the red one on the left from the. This is the main source that we have in terms of the X-rays. In fact, if you can see, mostly came from the Bremsstrahlung. And I don't know here. So what we exclude is this Bremsstrahlung subtracting this red curve, but above all, we wanted to avoid the prompt X-rays that comes at the beginning of the data taking. So if you look here, we have a lot of X-rays coming at the beginning, just after the trigger. So if you go here in the delayed region, we are less affected by the background. And the only background that we have here is this Bremsstrahlung coming from the electrons.
Are you sure that all the signals that you get at the end is the muonic hydrogen in the ground?
If you do the subtraction, yes, you have to do the subtraction between the blue line and the red one. So in that case, yes, we have just a signal.
And you're sure you know exactly the difference between the F0 and the F1. You don't get any mixture between.
No, yes, in this case, no, because you can see here the transfer rate comes mostly from the muonic atom. So okay, in this case, yes, you have also a percentage Okay. We do not distinguish between the F0 and F1 muonic transform to the IZ element. And then, yeah, sure, we have the background coming from the Bremsstrahlung. In that case, we can avoid the subtracting. I don't know if it's want to know. Okay.
Can continue later. Yes. So any other question? Yes, please.
Thank you. What's so challenging about the theoretical prediction?
But the challenging for the moment, they did simulation about the oxygen, but we are in touch with. Yes, I spoke with them recently, so we tried also to do a sort of brainstorming about the possible region of the flatness. So what we thought is, okay, in the oxygen, we are just a molecule of only oxygen. So here in this case, we analyze carbon, but it's methane, so it's in presence of hydrogen also. So what I thought, and this can be confirmed, I don't know, is that the presence also of the hydrogen could in a certain sense also shield the transfer rate from carbon. And what we have here so is a flatness due to the fact that even if we expect that the carbon transfer rate is decreasing, argue that due to the would be lower, and so on they compensate to investigate that. But I think that yes, next 2 weeks we can have some further results because it's something that we are working.
Nice progress. How good is your prediction for the line position?
For the line position, like the results, because for the hyperfine splitting, we expect.
Nobody gets the question.